Go.
Hello and welcome to another session of the IFIMAC plus ICMM joint seminar series. My name is Pablo San Jose and I'll be chairing the session today. On the virtual room, Elsa Prada will be the Zoom host. And as usual, the session will be recorded and then later it will be made available on YouTube. Okay, so today it is my great pleasure to introduce today's speaker, Héctor Ochoa, a former member of the ICMM, who will be telling us about sliding fluctuations in moiré multilayers. Questions are welcome at the end of the talk. Just you raise your hand virtually or in person. Also during the talk, short questions can be made or requests for clarifications. So Héctor is a young condensed matter theorist who's already done some very important contributions to the study of graphene and other 2D crystals, particularly on spin dynamics, magnetism, elasticity, and phonons, and on moiré superlattices. He finished his PhD on 2014 at the Autónoma University and the ICMM under the supervision of Professor Francisco Guinea. And during this period, he studied sources of spin relaxation, spin-orbit coupling, and scattering in 2D crystals, for which he received the PhD award of the Condensed Matter Division of the Spanish Royal Physical Society. After this, he moved to UCLA in California, where he expanded his expertise on spintronics and skyrmion physics in the group of Yaroslav Tserkovnyak, and he became an Ikerbasque Research Fellow at the DIPC in San Sebastian. Subsequently, he moved to Columbia University, where he is now an Associate Research Scientist. He's currently very active in the study of 2D moiré superlattices, such as the famous twisted graphene multilayers, which is the subject of today's talk. Héctor has an unusually strong trajectory for his age. He's co-author of 3 well-cited Nature Physics, 1 review of modern physics, and 1 physics reports. And I have to say, he's always impressed me with his deep intuition in physics and his mastery of group theory. And also by his bright and strong personality. Thank you very much for being with us today in person, Héctor.
Well, thank you. Okay. Oh, no, I have my own mic, right? Well, thanks, Paulo, a lot for such a nice introduction. And thanks, Elsa, for inviting me and the rest of the organizers and all of you for coming here in person. And I would like to thank also Paco, who hosted me in there these days. Okay, so I'm going to remove my mask if everybody's okay with that here in the room. So yeah, so I'm going to talk about moiré physics and twisted bilayer graphene. Most of what I'm going to say is pretty generic for these moiré heterostructures, but I'm mostly interested on the very interesting phenomenology of twisted bilayer graphene, and that's kind of the motivation for this study. So this is a list, you can see here in the right-hand side of the slide, a list of topics I would like to cover during the talk, and it's basically based on the context of these 2 papers. So just realize that the last time I was here in person giving a talk, I already talked about this work here. So hopefully I will not repeat myself much, but actually I think I have now like a more coherent message to give. And this is thanks to multiple discussions with Rafael Fernandez from the University of Minnesota, with whom we write this manuscript that I'm pretty happy with it. So you can check it out, and it will appear in physical review letters soon. It was just accepted last week. Okay, sure. Okay. So now you can see the whole figure. Okay. So now this is not working anymore. So now this is frozen. Okay. Now it's working. Okay, so this is oh, apologies for all this technical problem. So if I had to give like a 1-slide summary of the context of the talk, this will be this summary. So I guess the take-home message is that phonons of moiré superlattices are very different as compared to phonons of a regular crystalline solid. which is a pretty general and safe statement to make. So let me explain you what it really means. So something that I already discussed 3 years ago is that first, I'm going to focus on the collective vibrations of the moiré superlattice. So, and if we think about it, just from the energetical point of view, it's a very different physics as compared to a roller phonon, because we should not think of the moiré superlattice as a collection of masses connected by springs, but rather as a collection of strings, a network of strings under tension. And these strings are nothing but domain walls that separate areas of different, almost commensurate Bernard stacking of the two graphene layers. Okay, but what I wanted to make more emphasize today is actually on the on how these moiré superlattices respond to forces, to long wavelength forces, either internal, so that means forces between the two layers, which actually control this process of lattice relaxation, but they also actually discriminate between different regimes of dynamical response, which is what I'm trying to represent here. So basically, at the shortest long wavelengths, the system responds sort of like a conventional elastic manifold, like a conventional crystals, in the sense that under forces, the system relaxes by performing oscillations that are eventually damped. Whereas at the longest long wavelengths, the response is more akin to a fluid. It's kind of it's diffusive. And the separation between these two regimes is related to a new length scale that is associated with internal linear momentum relaxation processes between the two layers. I will explain that. I will also explain how the system responds to, there's already, I think, a question. So how the system responds to external forces, such as the one created by a quench distribution of disorder. And what I will show is that generically, the system is going to break into domains of this characteristic size. And beyond those length scales, the system resembles more sort of a glass or amorphous system. Okay, so we have this hierarchy of length scales in the problem, and in particular, these length scales longer than the moiré period that I believe probably for most of you are new, and that's what I wanted to explain, and how that can affect the phenomenology of two-step bidigraphy. Okay, so maybe we can check this. So there is a comment in the chat, so I don't know if there's a question or not. Anybody knows how to remove the...
Well, I was about to answer Walter, saying that indeed we don't have a pointer for the slides online, but the speaker has already been warned, and he will be saying to the left, to the right, and so on. Apologies for that.
Okay. I think if you just move the mouse to the right, eventually it will disappear. Okay, perfect. Okay, thanks. Okay, so I'm gonna start like reviewing like basic facts about twisted bilayer. So this is how the device looks like for at least for a theoretician. So we have two graphene layers, which is what these honeycomb lattices are representing here on the left of the slide, and there is a rotational mismatch between them, a small angle between them, and that creates this moiré pattern. So the electrons in the systems are sensitive to these moiré patterns because they jump, they hop from one layer to the other, and that reconstructs the electronic spectrum. So very flat bands are formed that naively you can understand just from band folding, but actually there is a particular alignment that is called the magic angle, which is around 1.1 degrees, for which this sort of localization or quenching of kinetic energy of electrons is sort of optimal. And it's precisely at that magic angle where all kinds of interesting phenomena takes place. So in particular, when you lower the temperature, you see all kinds of broken symmetry phases at low temperatures. which is what I'm trying to summarize in this diagram in the right-hand side of the slide. So in a sense, what happens is that when you dope the system, you put 2 electrons or 2 holes per moiré cell in the system. The system can host us up to 4 because we have spin and also the valid degree of freedom, which is approximately a good quantum number in the system because this moiré is it's long wavelength compared to the atomic distance. Then what happens is that gap opens in the system, a gap that you cannot understand from the point of view of single particle physics. And surrounding, and actually that happens at all integer filling of these flat bands. And surrounding this insulator, these domes represent areas where the system behaves as a superconductor. Okay, so this was the discovery of this physics, basically, by the group of Pablo Javier Herrero, like about 4 years ago. This phase diagram that I showed before, just from transport measurements. So the color represents in this figure in the left-hand side of the slide. The color represents the longitudinal resistance in a 4-terminal measurement. So this red state is a very resistive state that is actually an insulator. It has a thermally activated behavior. And these blue areas are actually the superconductors. So you have the typical characteristics here of the resistance versus temperature. And it's very difficult to measure Meissner effect in these 2D materials, but you have signatures of phase coherent transport manifested in this pattern of Fraunhofer-like pattern of interference. This is the color represents differential conductance. The x-axis is current. The y-axis is an out-of-plane magnetic field. Okay, so the way I understand this is if you take a vertical section in this lower right-hand side of the figure here, this is nothing but corresponds to oscillations of the voltage as a function of a flux or magnetic field, and this is the characteristic signature of superconducting quantum interference device, a SQUID. So basically, what this is actually telling us is that the superconductivity in this moiré system is sort of percolative. So the superconductivity is not uniform in the system, which is kind of, I think, an interesting point to make and to emphasize. And the reason for that is that because the devices don't look like this simplified picture that I saw at the very beginning, this is actually how it looks like. So this is a STM. I'm talking about the left-hand side figure on the top. It's an STM topographic image of one of these devices taken by the students of the group of Abhay Pasupati in Colombia. So you can see this is the moiré pattern, but you can see that it's different than the smooth moiré pattern that I showed before. You have like a very sharp AA stack areas, and you can distinguish here the formation of some domain walls that I mentioned before. So this is just due to forces between the layers that tend to relax the lattice to amplify regions of partial commensuration. You can see also that this is not perfect trigonal symmetry. There is some distortion in moiré pattern, and this is due to the fact that there are heterostrain or tensions accumulated between the 2 layers, which are almost unavoidable. And this is a long-range image of the devices taken by SQUID tomography. So basically, you are tracking the position of the Landau levels, and that allows you to estimate which is locally the density of charge that fulfills one of the flat bands. So, and this is related to the periods of a moiré pattern. So basically, what you are mapping here is locally the twist angle of the samples, and you can see that changes a lot through the sample, and this is just the numerical derivative of this landscape, and you see that the system breaks into sort of the domains with wild changes of the twist angle. This is one device. This is a second device. This is measurements from the group of Eli Theldov in Weizmann, and you can actually construct histograms from these local measurements, and this is the characteristic standard deviation of the twist angle around the magic angle. Okay, so more on this later. Let me just mention a last piece of phenomenology, which is kind of the motivation why I started thinking about phonons and this kind of stuff. So this is the what I call a weird normal state, or the weird metal of twisted Valier graphene when you have a superconducting device and you just raise the temperature, or you kill the superconductivity with a magnetic field. So this was first observed by the group of Pablo Jari Herrero. This is the image on the left, and you see a very nice linear in temperature resistivity that eventually the system becomes a superconductor. But if you kill the superconductivity with a magnetic field, you see that this linear scaling can be extrapolated down to very, very, very low temperatures, to temperature scales which are not obvious in the problem. Okay, this kind of the mysteries, and this is the so-called strange metal behavior. This is a terminology borrowed from the cuprate. Okay, and usually strange metals are bad metals. So bad metal is also a very resistive metal with a non-Fermi liquid kind of behavior that actually doesn't saturate when you raise the temperature to the so-called nominal Joffre-Regel limit. But actually, and this is data from Efetok's group, I'm talking about the image on the right, actually this linear resistivity always saturates with temperature. To the nominal, and that doesn't depend on the actual power law with temperature or doping or anything. It's a universal behavior in the devices. It always saturates when, basically, according to the analysis in the supplementary material of this paper, when Kf is comparable to the inverse of the mean free path, or basically when the resistivity starts to be comparable with the quantum of resistance. Okay. So it's a weird metal because it's a strange, but it's not bad. So that's my definition of a weird metal. Okay, so this is kind of my line of thought when I saw this data, and this is how I try to understand this physics. No, so the question to me is, and I think it's a very interesting question: what is the nature of the parametallic state of the twisted bilayer graphene? And another way to frame, a more specific way to frame this question will be, are electronic quasiparticles well defined, for example? And my answer will be yes, because there are clear evidences of the existence of a Fermi surface, for example, in magnetotransport. Most theoretical models start from a Fermi liquid with a Fermi surface. And actually, this saturation with the Joffre-Regel limit, what it's telling us is that transport in principle is mediated by coherent electronic quasiparticles. So then the question to me is to find a scattering mechanism that can explain this linear behavior with temperature, which is something that generically you get from classical equipartition when you have scattering of electrons due to any bosonic fluctuation, particular phonons. Now, the question is, how can this classical behavior if this classical behavior can be actually extrapolated to such a low temperature, okay, which are not naively these scales are not small in graphene, because graphene is a pretty rigid material, so the sound velocity of phonons is large, etc., etc. So these are some options that I listed before. So since basically this temperature scale is determined by the kinematics in the Fermi surface, it could be that there is a very funky Fermi surface reconstruction. It could be, and this is kind of the point of view that I'm going to emphasize at the end of the talk, could be that the spectral weight of these bosons actually is moved to very, very low energy. It could be a combination of both, which is basically what happens when you have electrons coupled to critical fluctuation. Or neither of them, and therefore what I just said is all bullshit. No? So these are the only options that I see. Okay. So this was kind of motivation. So let me start with the real stuff. I'm gonna take my cell phone because I don't know how I'm doing in terms of time. Okay, I'm doing fine. Okay, so stacking and phasons. Let me explain what these words mean. So stacking is pretty obvious. So by stacking, I mean the vertical atomic arrangement of the two layers that is going to modify the band structure. Okay. So the way I'm going to parameterize different stacking configurations is in terms of a two-dimensional vector. So my reference in configuration space is what I'm going to call AA stacking. So that corresponds to this configuration. So atoms in the same superlattice in both layers lie on top of each other. And by shifting one layer, let's say top layer, with respect to the bottom layer vector equals to a nearest neighbor vector, for example, then that produces AB stacking or Bernal stacking, which is actually the minimum energy configuration. And you can see the tunneling rate and also the phases that the electrons grab when they hop, the phases that Dirac electrons pick up when they hop from one layer to the other actually changes, and that changes completely the low energy electronic spectrum in these two systems. So the way I understand a moiré system is just a system in which, in real space, the system is exploring all the possible stacking configuration, which is a true rigorous statement when the system is incommensurate, which is what happens in general. At the small twist angles, when this moiré pattern is large, actually it's a pretty valid statement. Within the moiré cell, the system is basically going to explore all the stacking configurations, and that is given by this kind of function. So this function is telling me, as a function of the twist angle, which is the local stacking configuration parameterized in terms of these 2D vectors in a given point of space. Okay, and from this you can actually see, you can identify here which is actually the moiré period in terms of this twist angle. So this is a way to construct the so-called continuum model that I'm not going to discuss much because I'm not going to talk much about electrons in real space. So this is basically the tunneling matrix in sublattice space, in the space of Dirac electrons or Dirac spinors of the 2 layers. So it's a matrix in sublattice space. And basically what happens when the electrons hop from one layer to the other, they pick up a phase that is related, which is the notation I'm trying to show here, is related to the shift in momentum space of the position of the Dirac points of the 2 layers. Okay, and this phase is actually a function of the local stacking configuration. So this is a way to construct or to understand the continuum of the Strichter-McDonald model in real space. Okay, and this is also a way to understand how fluctuations, deviations from a rigid stacking configuration, a rigid rotation, how that couples and how to electrons and how that affects the electronic dynamics. Okay, so this is a way to understand stacking configuration in terms of the phases that electrons pick up when they hop. A more straightforward way to understand this stacking field is in terms of mass density. So the moiré pattern is nothing but an interference pattern because we are basically summing 2 periodic functions corresponding to the distribution of ions in the 2 layers. And the form of this, the total density, is going to be of this form. So there is a modulation of the amplitude of this mass wave that is precisely controlled by the stacking configuration. So if you plug the expression that I showed before, you just end up with the typical expression for a moiré pattern, where this modulation that I'm representing here in the bottom figure is given by the vectors corresponding to the difference in the reciprocal lattice vectors of the 2 layers. So the information about the angle is either encrypted here, if I have like a momentum space picture, or here in this real space picture. But the point that I wanted to emphasize with this kind of trivial construction is that there are actually 4 phases freedoms related to the relative position of one layer with respect to the other and in space that basically parameterize physically different but energetically equivalent mass densities. So one is just the center of mass of the bilayer, so it's like a rigid translation of the bilayer in the space, and that is going to be related to an acoustic phonon. But there is also a hydrodynamic degree of freedom related to the relative translation of one layer with respect to the other. That is going to change the reference of coordinates in the amplitude of the moiré. So that is going to translate the moiré pattern in space, sort of. And this is the so-called Phasons. Okay. So I need a bit of water. So this Phason degree of freedom, this is the phase I was referring to in the title of the talk. And Okay, so with these pictures, I'm going to try to explain why this is an acoustic mode. So for example, if we consider a bilayer, it's a cartoon picture of my bilayer that is in a commensurate state. So for example, Bernal bilayer graphene, which is not exactly like this, but okay, for the sake of the argument. So if you now slide one layer with respect to the other, that is clearly going to change the configuration of the system. That is going to cost energy. So this mode is actually an optical form. Okay. But now if the system is incommensurate, which is what I'm trying to represent here, this will correspond to a rigid rotation of the two layers. Then when I slide one layer with respect to the other, sure, the system is different, but actually there is no energy cost because, as I said before, the system was already exploring all the stacking configurations, and the new system is still exploring all the stacking configurations. So there is no free energy cost associated with this. And this is kind of obvious in a sense because these are just an example of two floating layers. So I'm not, coupling the two layers. So basically, this is another way to write down the phonons, the acoustic phonons of the two independent layers. But this is still true when the two layers are coupled and there are forces, van der Waals forces between the two. What happens in this incommensurate situation is that now the system, what it's going to try to do is, in order to minimize the van der Waals energy, it's going to create or to expand regions of partial commensuration, and to the cost of creating some doming walls, some solitons that are going to be the borders of these almost commensurate regions. And this is the typical physics of a frequent control model. And still, you have plenty of possible solutions which are degenerating in energy. And but now this phase freedom is not longer a rigid translation of one layer with respect to the other. Is the sliding motion of this soliton, and this is a more complex atomic rearrangement. And this is in this complexity is where all the interesting physics comes. Okay, so let me show you. So this is the cartoonist picture of all this physics. Let me show you a couple of equations. So this is the model. So basic elasticity model that basically everybody employs. It's a free energy model which contains two terms. One is just the elasticity, the conventional elasticity of the two graphene layers in terms of some Lamé coefficients, some elastic constants. And there is a stacking potential representing the van der Waals forces, which is going to be a periodic function on stacking configurations. And this periodicity comes from the fact that in my description of different configurations, if I start from A stacking, I just slide one layer respect to the other vector of the Ravel lattice. Of course, I end up with exactly the same kind of configurations, and necessarily this potential has to be periodic. And now the minimization of this free energy, I'm going to get, which is actually the stacking texture that minimizes this free energy, and this is the same as solving this equation that equals the van der Waals addition forces to the stress. And this is the first step. So this is the problem of lattice relaxation. The second step will be to study harmonic oscillations around this free energy minimum. Okay, and that will be given by some static susceptibilities. So it's basically what I'm going to compute is some difficult but still easy to deal with matrix form of second derivatives of the free energy with respect to this stacking field. Okay, so this is the potential on the left hand side. I'm representing the potential landscape in configuration space. So this is just this function that is periodic, as I said before, in the Phys variables. And if you translate this to a rigid moiré lattice, this is actually how the van der Waals free energy landscape looks like in real space. So in the problem, so the competition between these two terms in the free energy actually it can be described in terms of the competition between two length scales in the problem. One is the moiré period that I already introduced, which is the periodicity of this landscape in real space. The other is actually the length scale that describes the competition between these two terms, which is given by some elastic constant, in this case the shear modulus, because most of the strain is going to be shear in this relaxation process, compared to actually the second derivative of the on the van der Waals potential around a minima, AB or ABA stacking configuration. And this defines a new length scale that is the characteristic width of these solitons, of these domain waves. Okay. So that's what the system tries to do, tries to expand these areas of partial commensuration and shrink to these areas of A stacking, and creates these domain walls with this characteristic width. So this is the cartoonist picture. Let me show you a calculation. This is a calculation that I did a while ago, and you can see many people have basically implemented the same kind of methods in the literature. So this is probably an incomplete list of references. So this is the way I do the calculation, which is basically what I think everybody does, which is I write an answer for this stacking texture. This is the real rotation, and I add a relative displacement that I'm going to find this displacement that actually minimizes this free energy. And the only constraint that I'm going to impose is to assume that in the Fourier harmonics of this strain field, that preserves the symmetry of the moiré pattern, in particular translational symmetry of this moiré pattern. And what I do is just to include enough number of harmonics here, and this is how the different harmonics scale as a function of the ratio of these two length scale, which is basically the only free parameter that I have in the system, which is in turn given by the inverse of the twist angle. And the colors in the right-hand figure corresponds to the momentum cells that are represented in the left-hand figure here. Okay, so this is the evolution. You can see the magic angle corresponds roughly to this value of this ratio. So you can see there is a change of monotony around the magic angle, completely unrelated with magic angle physics, but it's related to the fact that around the magic angle, these domain walls start to be very well defined. So this is how this function looks like in real space. So this is the displacement field that have this kind of vorticity associated with the chirality of the system, the fact that we are rotating one layer with respect to the other, and that introduces certain hardness in the system. And this is how it looks in real space. So basically, what the system does is already what I explained, to shrink these areas of A stacking, expand these dark areas of AB and BA stacking, and form these domain walls. Okay, so that's the first step of the calculation. Second step is to compute the phonon spectra, now associated with out of phase oscillations of the two layers. So this, I'm showing here calculation from Mikito Cosino and his student. I did similar calculations, but not so nicely, I think. So that's why I use their figures. The way to understand this calculation is just we have the acoustic dispersion of the acoustic phonons of the original graphene layers, and we are just folding back these phonons to the new smaller Brillouin zone of the moiré superlattice. And now this van der Waals interaction evaluated at the so now we have a very much sharper stacking texture because of relaxation. So that is going to produce several unclap processes between phonons that are going to open Bragg gaps at the zone centers, and I'm going to produce this kind of spectrum with many optical phonons, but still two acoustic phonons, and that is the Phason. And the Phason is nothing but the the kind of the elastic distortion of the moiré superlattice. There are interesting things in this calculation is that now the transverse Phason corresponding to this polarization actually is more energetic than the longitudinal Phason. And there are different ways to understand this. The way I understood this is by writing down like the effective elasticity for a moiré pattern, which is an expression like this. And there are many interesting things here. So for example, so up to here, the first two terms in the first equation represent regular elasticity of a crystal, but there's a new elastic modulus, which is associated with the fact that, as explained before, translations of one layer with respect to the other are sort of soft, but rotations of one layer with respect to the other, those cost energy. So there is a new elastic modulus associated with this costing energy. And there is also another interesting thing that when you are in the limit of these soliton networks, actually the first Lamé coefficient is negative, which is weird. It's totally allowed because the sound velocities both are positive. So the shear modulus and the bulk modulus are both positive. but one of the Lamé coefficient is negative, and this is like an elastic manifold with a negative Poisson radius. And this is a generic feature of incommensurate lattices. And it's basically due to the fact that the energetics scale linearly with the distance between this sort of atoms. It's precisely because the energetics are described by a network of solitons under tension. Okay, so that's this. Let me move on to new stuff that I think is more interesting. Let me talk about disorder and twist angle disorder. So I have an animation here that I lost when I export to PDF. So you have to, bear with me, right? So I'm going to try to explain this with my hands. So I'm going to consider now disorder in my graphene system, disorder that is going to be embedded in the lattice. What I mean by that is that, for example, in the figure on the left, these dark points are representing, for example, vacancies or atoms that are chemisorphed to the graphene layer or whatever. By embedded, I mean basically when I take my crystal and I move my crystal to the other corner of the room, the energetics don't change. There is no energy cost associated with that. So that means that embedded disorder doesn't break long-range order in a crystalline lattice just because of this fact. What happens in the case of the moiré? Same situation, right? Embedded disorder in the two layers, but now, and this was the animation that I lost, when now I slide one layer with respect to the other, what is going to happen is that the moiré pattern is going to be shifted in positions. So now the position of these defects are going to lie at different locations of the moiré pattern. And the moiré pattern is giving us an idea of the local van der Waals energetics. So now relative changes of one layer with respect to the other in the presence of disorder, that changes the energetics. What happens then is that disorder is going to break always long range and stacking order in the system just because of this fact. Okay. What's the meaning of that? The meaning of that is that if I compute, for example, disorder correlations between the tunneling matrices, which is basically correlations between the phases that atoms grab, which depend on this local function, these correlations are going to decay always exponentially on a certain length scale, which is actually universally determined by the fluctuations in twist angle. By universal here, I mean that it's basically independent of the model of disorder. So it's a generic statement of light, regardless of the specific form of disorder. Okay. Now let me explain this with a couple of equations for a particular model. Okay, so this is basically linear response theory. So I have a distribution of forces created by disorder, and that is creating some variations in the stacking, some fluctuations of the stacking configuration locally, and that is determined by the mechanical susceptibility, which is the tensor that I have already calculated when I compute the phonon spectra. And I need a model for these forces, so I'm going to consider forces like this. So basically depend on gradients of potential. So this is a way to make the statement mathematically that my disorder is embedded in the two atomic layers, okay? Because the forces enter through gradients, okay? And I'm going to consider a Gaussian distribution for these disorder potentials, conventional theory. And I have two relevant parameters here, basically the strength of this disorder and a characteristic length scale that determines which is the range, the space range of these random forces. Okay, so that's the model. And now the only thing I have to do is basically to compute fluctuations of these stacking fields. And you use linear response theory, the expression that I used before, and basically the expression is given by something like that. So the response is going to be dominated by these soft Phasons modes, which are divergent in the limit of a small momenta. So that gives me a q to the 4. And now this in the numerator, I have just the momentum, the Fourier transform of the correlation of these forces. And now what happens when you compute, you calculate this? Of course, this momentum is now defined in the smaller brilliant zone of the moiré superlattice. When you do this calculation of these correlators, it matters a lot if we have interaction between the layers or not. Basically, it matters a lot if I have lattice relaxation or not. if there is no interaction between layers, actually this scales as q to the square, and therefore this goes as 1 over q to the square, and we have quasi-long range order. But now in the presence of lattice relaxation, there is a finite component at 0 momentum. So this diverges as 1 to the 4, and we recover the usual IFIMAC criterion. So long range order, as I said in the previous slide, is lost on some length scales. Okay, so this is the actual calculation of the 0 momentum component of the correlator of forces as a function of the ratio between the moiré period and the width of the domain walls, which is basically the inverse of the twist angle, as I said before. So you have this depend. Oh, okay. First, this is measuring units of the parameters of my disorder model. Only one of the potentials that I consider that were the ones associated with twist angle disorder. This is the contribution that is most important, basically because the stacking texture of the relaxed lattice structure contains mostly shear components of strain. That's why. So this grows quadratically with this ratio, and around the magic angle it starts to saturate. This is reminiscence of the behavior of the Fourier components that I showed before, and this is because starting at this magic angle, the solitons, the domain walls, start to be well defined. So another way to visualize this in real space is that basically we have very short range components of these random forces that are coupled to the domain walls that are pinning in real space. They are pinning the domain walls, and that is the reason why beyond this collective pinning length, you lose long range order. Basically, the system ceases to respond elastically to external forces. In order to explain this disorder landscape that I showed at the beginning, you just need to consider random forces which are of the order of the tension of these strings, of the tension of these domain walls. It's a pretty reasonable number. Okay. So this is basically what I'm saying. Now, if you integrate the correlator of the twist angle, which is basically an antisymmetric derivative of the stacking field, up to, you have to integrate that up to some length scale, which is precisely the spinning collective length scale. And then you see that basically the parameters of the disorder potential disappear, and you have this sort of a universal relation between stacking fluctuations, the moiré period, and this length associated with disorder. Okay, so for example, if you take for the fluctuations the standard deviation of these histograms, that gives you length scales of the order of 200 nanometers. That agrees well with this picture. And actually, it's something that I noticed preparing the slide. If you divide the quantum of magnetic flux by the square of this length scale, you get this magnitude of magnetic field, which is basically the period of this oscillation of this Fraunhofer interference pattern. So basically, this length scale determines the characteristic size of these sort of Josephson-Jackson, this kind of discrete devices that effectively you have in the system. Okay, so let's move on to dynamics now. So I'm considering now the dynamical response of the system. So basically, I'm going to consider the dynamical susceptibility, or if you wish, the Phasons propagators here. They are going to adopt, this propagator is going to adopt this generic form. So this is the static susceptibility, that is the matrix that I diagonalized before. So this contains sound velocity, things like that. And now all the information about how these Phasons are coupled to the rest of the world, basically, is contained in this memory matrix, or if you want to think of this in terms of usual diagrammatics, is a self-energy for the Phasons. Okay. So now, basically, symmetry, just as in the previous case, impose how is the form of this self-energy of this memory matrix at the small momenta and small frequencies. So if there is no interaction between the layers, basically that's a statement that is telling you that the linear momentum of the two layers is conserved individually. And therefore, because the relative momentum of the layers is conserved, this memory matrix has to go to 0 with momenta, with a second power. The prefactor, the coefficient, is what we call viscosity. Okay, so that's how dissipation enters usually for acoustic phonons in a crystal. But this is not true because there are forces between the layers. Okay, the relative momentum of the layers is not conserved. So actually, for our problem, this is finite at the small momenta. And what that means is that now, if I go to very small momenta for these phasons, what happens is that the imaginary part of the pole of the propagator is going to start to be larger than the real part. In other words, the phason is going to become overdamped, which is what I'm trying to represent in this density plot, which is representing the imaginary part of the susceptibility as a function of frequency and momentum. And you always enter in this diffusive regime. Maybe it's easier to understand this with these vertical sections. So when you are here, basically you have more or less well-defined quasi-particle pole. When you are in this diffusive regime, you have like a very broad central peak at a 0 frequency, which is a characteristic of a diffusive response. Okay, so this is kind of the general argument. Let me show you actually how it works in a calculation. So this is the stacking potential that I showed before, this density plot that I showed before, this function that is periodic in a stacking configuration. And we can span around the equilibrium solution, this lattice relaxation problem that we already solved. The harmonic term, the quadratic term, is something we already solved. And the first correction, the first anharmonic correction, comes from these 3 phonon processes. Okay. So basically, this friction, this overdamping of these phasons comes from anharmonic fluctuations given by in the leading order to this kind of cubic interaction. So this is actually how the calculation looks like. So basically, you can write down sort of a Green-Kubo formula for this memory matrix. In terms of diagrams, it's this and this is the force associated with this cubic term in the free energy. In terms of diagrammatics, it's this kind of self-energy diagram, okay, where the vertex represents this cubic interaction, okay. And the result of the calculation is that indeed the 0 momentum, 0 frequency limit of the self-energy is actually finite. This is actually the result. You can interpret this as a sort of relaxation time. So it's the time, the characteristic times in which the relative momentum, linear momentum of the layers relaxes due to anharmonic forces between the 2 layers. Okay, and it's given basically by resonant processes in which one of these amplitude or optical modes is scattered into other through or by a Phasor mode. Okay, it's a function that the classical limit grows linearly with temperature. So you see that these optical phones are anharmonically coupled to these phasons, and they act as a sort of a dissipative bath for the phase, and they introduce some friction in the process. Okay, so yeah, just to conclude, and I'm thinking I'm doing good in terms of time. I'm gonna discuss very quickly 2 physical consequences. One is kind of obvious. The other is just a speculation, but yet since I'm among friends, I think I can speculate. So another way to see this overdamping, or to understand this overdamping, is basically what is happening is something that I mentioned at the very beginning of the talk, that we are transferring the spectral weight of these phasons from higher energies to lower energies. That's what dissipation generically does, but in a very dramatic way in the case of this frictional damping. So this is the density of a state that you can compute from the static and the imaginary part of the dynamic susceptibility in this way. The trace is just summing over all modes and momenta and all that. So in 2 dimensions for an acoustic phonon, no damping, no dissipation, you have a linearly dispersing, linear density of states. When you include a lot of viscous damping, there is transfer of spectral weight to lower energy, so the density of a state is always finite at 0 energy. Okay, but this transfer is very dramatic in our case because of this frictional damping, just due to the fact that basically all these phasons become overdamped. And you have actually in 2 dimensions a logarithmically divergent density of states at 0 frequency. Okay, so what are the consequences for that? If you now compute the specific heat at constant stress, generically at low temperatures, you are going to have always a deviation from the bylaw. And this is just due to the fact that you have a finite density of state at 0 energy of vibrational mode. So this is in the figure on the right, what I'm representing is the ratio of Phason contribution to the phonon contribution. At low, very low energies, this is a characteristic time scale defined by the moiré pattern through the dispersion relation. So this at low temperature, very low temperatures, the Phason contribution always dominates. When you start rising the temperature, other optical amplitude modes are going to start to contribute, and this sometimes gives rise to this sort of bump that is called, in the context of amorphous materials and glasses, this is what is called the so-called boson peak. And in the low temperature Phason dominated contribution, the scaling is like that. So this is the logarithmic divergence that is basically now cut off by the collective pinning length that I introduced before. This is analogous, and this analogous formula to, for example, which is the contribution to a specific heat of vortex fluctuation in the mixed state of Player superconductors. It's basically the same system, and it's just due to incommensurability. So this is kind of the message, no? So you have now the varying density of a state that gives a very large specific heat at low temperatures, very fast entropy production. And this is kind of similar to what happens in other amorphous materials and glasses. So I think that's an interesting observation. So this is calculation that I just did a couple of weeks ago. So I don't know. I think at some point maybe we will write down something about this. But this is the most. This is the speculative part, and I think I'm going to conclude with this. So how this could, I'm not saying is explaining this behavior, but could explain this strange or weird metal behavior that I described before. So according to FETOF data, resistivity is scaling to when Kf times L mean free path is smaller than or larger than 1 or comparable to 1. So in principle, I could use semi-classical Boltzmann transport theory. So my resistivity is going to be given by an expression like this. This is just a kernel of the solution of the linearized Boltzmann transport. You can understand this also as a functional that you minimize, and that's the resistivity of your system according to the erratic theorem. The important piece of information about the boson fluctuations is contained in this scattering kernel. Then you can write in terms of the coupling G and the imaginary part of the susceptibility. That is what I've been talking about in this last slide. So the observation is the following: at large enough temperatures, you can approximate this by the classical limits of the Bose functions, and then you have something that scales linearly with T. What is large temperatures? Well, if we assume that the scattering is quasi-elastic, so basically you're scattering electrons from one point of the surface to the other, basically it is a natural cutoff of the maximum momentum transfer in this scattering process, which is about twice Kf. So it's basically the phonon dispersion, if there is no dissipation of damping, is the phonon dispersion evaluated at 2 Kf, what gives us a characteristic energy scale beyond which this susceptibility is basically suppressed when quasi-particles are well defined. But actually, if quasi-particles are not well defined, these peaks always move to the left because there is this transfer of the spectral wave. So these temperature scales, which are always of few Kelvin, several Kelvin, because the sound velocities are still large, there is only a 30% reduction of the sound velocity of Phason correspond to the with respect to the phonon, and the sound velocities of the phonons of graphene are large because carbon is very light and graphene is very stiff. So these are very large numbers, and that's the mystery, how you can extrapolate this behavior to very low temperatures. The reason maybe is that, well, this is not the characteristic temperature scale of the problem, because all the spectral weight of these bosons are moved to much lower energy. So maybe this classical behavior could be extrapolated to lower temperatures. That's kind of the speculation. Actually, there is more to that, because basically all these physics that I have explained is due to the fact that these phasons are acoustic phonons, sort of Goldstone modes, that are associated with an invariance of the free energy, but because of incommensurability, not because of a true microscopic symmetry of the microscopic Hamiltonian. So meaning that these Goldstone modes are not truly Goldstone modes. They are not protected by a conservation law. That's why they become overdamped. So for the same reason, there is no fundamental reason why the coupling between phasons and electrons should be through gradients of this Goldstone mode field, or in momentum space, the matrix element of the coupling for a boson Goldstone mode should go to 0 when the momentum goes to 0. But in this situation, I don't see a fundamental reason why that should be the case. One possible mechanism is by dressing this vertex with an harmonic fluctuation, just like in the calculation in the previous case. And then you have a coupling that is temperature dependent. But now the problem starts to resemble or starts to include many ingredients of the problem of electrons coupled to an antiferromagnetic quantum critical point. So you have sort of criticality without a quantum critical point, just because of the fact that these systems are quasi-crystalline. That's the speculation. So I don't know. And that's the end. That's the end of the talk. Perfect on time. I'm very proud of myself in this moment. So yeah, so take-home messages, which are the collective acoustic modes of moiré superlattice. These are called phasons, are fluctuations of the phase of the moiré mass density, or the amplitude of the mass density. You can understand this also as a coherent superposition of optical phonons that describes the sliding motion of stacking domain walls. And in general, this motion is diffusive rather than in propagating waves at long wavelengths due to an harmonic fluctuation. And what are the sources of disorder in moirés? Is this phase spinning, which is a generic phenomenon due to the quasi-crystallinity of the samples. And with this, I just conclude, and thank you for your attention. And thank you for me.
Thanks a lot, Héctor. Okay, so it's time for questions. I guess, Elsa, we start with questions in the room. Anybody has questions here?
Yes, please.
Yes, there's one question.
Thank you, Héctor. Great ideas. So
Okay,
my question is very generic. Is in all this discussion, electrons were like non-interacting. So would a strong interaction between the electrons alter this picture?
So one naive way to alter the whole picture is that is this idea that electron correlations are going to change. So I just draw like a very simple circle for the Fermi surface, but this metallic behavior could coexist with broken symmetry with, for example, a nematic. The state could be nematic, which is there are experiments that suggest that this metal is nematic. Could be coexisting with charge density waves or with some kind of order, and that is going to change completely the geometry of the Fermi surface, and also the form that the Fermi surface electrons couple to phasons. So you could have certain hotspots where the coupling in certain areas of the Fermi surface is stronger than in others. That is going to short-circuit your scattering mechanism, which is basically what happens close to an antiferromagnetic critical point. And that changed completely the kind of arguments that I've been invoking. So then the low temperature resistivity could have a very difficult to describe temperature dependence just because of that. So this is just a nice way to see how strong correlations, strong interactions could change completely the picture. So it's a very difficult question to answer.
More questions here? I have a question, just a clarification. So the idea is that the idea that you're proposing here is that these boson phason modes could be explaining the anomalies, the weird metal property. So if I understand correctly, the introduction of defects is necessary or is a problem to explain?
No, that's a very good point, because it's probably not sure if it's necessary. I don't think it's not necessary. The overdamping of this phase and the fact that they become overdamped, it's a generic fate, regardless of, I mean, it's just it's an intrinsic property of the system. You only need to invoke forces between the layers, van der Waals interaction, no disorder there. Now, your point is, well, it's a good one, because another way to interpret this collective pinning length is that now the Phason is not going to be acoustic anymore.
Exactly.
It's going to be gap.
This was the point.
This gap, if you put the numbers, is small. So,
okay, so you could
for the character, so the samples are good enough to
not see this scale.
To still exactly. So this temperature scale is very small, but there's another relevant temperature scale in the problem, just coming from this order. And if
your estimate for this?
Yeah, put the numbers on the paper for sure. I forgot, but it's below 1 Kelvin, I think. Yes. So let me check. I just put in the it's a small number. It's a small number.
Okay, so a second follow-up question to this. So you're assuming throughout that your system behaves is well described by continuum theory. So if you go back to the beginning and think about the Franke-Kontrova model, you're assuming the floating phase, but there is more to Franke-Kontrova. So this is devil staircase with local commensuration. Does this also gap?
That will gap, definitely. That will gap the Phasons. Now, why I'm invoking this picture where I'm starting from a floating phase and then I start to contract? The reason is, so we have moiré period, the domain wall width, which is the competition between these two energy terms in the free energy, and then the interatomic distance. If the domain wall width starts to be comparable with the interatomic distance, then you're in problem. Now, what is the domain wall width? It's several nanometers.
Yes.
Why? Because the van der Waals interaction is very weak, whereas graphene is very rigid. So I think these ideas and this continued description is still valid here.
Okay, yes, I agree.
But now, if you now include the disorder, I mean, the situation is, but that's basically what disorder does. It's generically to pin the system. So by the same kind of argument. So yeah.
Okay, great. More questions here? No. Okay, Elsa.
Yes.
Any questions over there?
Yeah, we have a couple of questions. So first, Lenny, please unmute yourself.
Okay. So first, thanks for the talk, Héctor. That's been very nice. I have two related questions. It's related to the strange metal behavior. So regarding your results, so my question is whether you expect some kind of characteristic top independence of this strangeness. And the other question is when you say that the resistivity saturates, do you know if they have had into account the possibility that there is conduction through higher energy bands? Because I remember that at the beginning, this was proposed that there was this decrease of the resistivity.
So let me answer the second one, which is easier, I believe. So I think they discard the possibility of thermally populating higher energy bands because basically, so this saturation was universal, and they were able to extract, the characteristic Fermi wavelength because they know the concentration of carriers and the emit-free path. So I forgot, but that's kind of the analysis that is in the supplementary material of this archive paper by Fetov's group. So that was their argument, actually. And I think it's very suspicious that the saturation is always, never exceeds the quantum of resistance. So to me, let me put it this way. Regardless of which is the mechanism, I don't think there is, the data doesn't support the image of incoherent electronic transport. This is another way to put it. So for simplicity, I am going to assume that you still have more or less well-defined quasi-particle. But that was also their claim. So I think that's the analysis of the supplementary. Maybe I should go back to the supplementary material, or maybe in the process they have changed something. I don't know. But that's in I think their paper. To the first question, very difficult to answer. So I guess the arguments that I present are just to justify why, in a very simple phonon or Phason or whatever, limited resistivity theory, you can actually extrapolate this behavior, classical behavior, to lower temperatures. But I don't have a theory for the resistivity, and I think it's going to be very difficult to explain all the features. Now, for the density dependence, it could be related to Helly's question, in the sense that by changing the doping, you can change dramatically actually this metallic phase. So that could be a possibility, that the scaling with temperature or lower temperatures is just changing because of some broken symmetry and some reconstructed Fermi surface, and still this kind of simplistic picture based on Boltzmann transport theory still holds. So I guess that will be my answer, but I don't have an answer for you because I don't have a theory. So yeah.
Okay.
Okay, and then there is another question by Walter Arnold, which is written: are there measurements of the specific heat in order to check the amorphous-like properties?
So as far as I know, they are not. And I think it's probably very difficult to measure specific heat. But as far as I know, there are no data out there. So maybe somebody in the audience knows more about the literature, because sometimes it's difficult to follow. But I think there is no measurement of specific heat.
Okay, thank you very much. I think there are no more questions, and we are already more than 10 minutes past the time. So I think we are going to conclude here, and we can, of course, keep discussing after I stop the recording. Thank you very much, everybody, for your attendance, and see you next Thursday. Bye.
Thank you all. Bye-bye.